Are you here? If you are, you can actually unmute yourself and start sharing your video.
It's always slightly scary to start to unmute myself because we've got lots of people listening. So can you hear me and can you see me?
We can hear you. We cannot see you yet.
Okay, my message is you can't start your video because the host has stopped it.
Oh, wait. So that means
Wait.
Allow, no, yeah.
Let me put my hat on, shirt on, throw the
please,
cats out of the room.
Do get dressed.
Be decent.
We don't care about cats. Yesterday, Alan Page actually did his whole presentation with his dog sleeping behind him.
I saw so sweet.
So you're not going to be any weirder than Alan.
Yeah. I don't have a sofa in here, so I can't have a dog. I don't own cats. My children are out, so it's all fine. This is just my office. Let me just see if I can start video again. Oh, is that me? Looks like me.
Yeah,
looks like
it's you.
Yeah, excellent. With bigger lockdown hair.
Now,
okay,
I'm gonna stop my. I should stop my share, and now you can start your own share, and we will be able to start your.
Well, I'm going to use a thing called Minicam because hopefully you can see a slide up in the top corner of my. Oh, for goodness' sake! It's like working in a mirror. You can see a slide in the top corner of the screen. Is that right?
On the top right of the.
Yeah, there we are.
Great.
That's good, and now, I can flip over to slides if I need slides, and I will, but the point of this is not that it is a particularly slide-driven thing. This is, I hope, a bit more interactive, and so in the middle of that slide you can see a web address, and I'm going to see if I can generate a web address mid-screen without looking too ridiculous. There we are. So hopefully you can now see my web address, hear my voice, see my slides. All of these things are happening at the same kind of time. That's where the materials are, because this is as interactive as one can be without being able to see the audience or hear anything you can do. So I've got the chats up in front of me and I'll have a look at the chats. I might be able to go into Slack, but I'm kind of one screen further down than I should be, so Slack might not be the best place to contact me. We're going to look at basic pathologies of simple systems. And that title in itself is clickbait. Sorry. Well, it is clickbait because most titles are clickbait, and I'm going to show you something not that is a complaint. Here are a bunch of basic pathologies of simple systems, but we'll go into what the basic pathology is and how you as a tester can recognize what's happening to you and adjust yourself so that the basic pathology, the things that simple systems do that confuse us, won't confuse you, I hope, quite as much, or won't surprise you quite as much, because our job as testers is to search for surprises and to find them before they become unpleasantly expensive surprises. So that's what we're going to do. We're going to look at the basic pathologies of simple systems, and as I say, that one's clickbait. The pathology is not in the systems, the pathology is us. We are surprised and confused by simple systems. Now, at this point, I want to pay tribute to Robert May, who died at the end of last month. He was an Australian mathematician, worked in the US and in the UK, particularly at Oxford and Princeton. He wrote in 1975, he wrote a paper on complex systems. And this was an early paper on complex systems. And in it, he didn't just show how simple systems could be really weird, but he promoted something that I think has infected lots of stuff that I've looked at since, from Hofstadter's Gödel, Bach and onwards. And that is the idea that even simple little systems are odd, and that in order to understand that oddness, we should play with these systems. We should have fun with them. We should understand how odd they are, then they won't be odd to us, and the pathologies then go away. So that's why you've got a web address. You've got a web address because this is a clickbait title. The pathology is us. We mistake simple systems for systems that are easy to understand and predict. And in order to get over that, we need to play. And in order to play, I've given you my small contribution to this wide-ranging debate, wide-ranging conversation about playing and software. So this is Rob May's more complicated 1975 statement. I want you to remember, if there's one thing you take from this, it is that some simple systems don't have simple properties. Some simple systems are surprising. And I want us to get in amongst that and to understand what's going on with that. As an aside, I'm going to just flip over to big slides because we're going to start needing to read things, because I do have a few more words than this than usual, so forgive me while I wrangle my kit. Put things in chat if you're not able to read this. I hope you are. I hope I've increased my resolution such that it is good enough. Do we build or test simple systems? Because I get people say to me, well, I don't do simple systems, I do complicated systems, and I understand my complicated systems fully, and I go, wrong. But let's briefly kick that one around. We do build simple systems. I'll show you how simple. I've had a degree of complexity in building these simple systems, which you may see because I've left a bug or two into my frustration. I introduced them this morning, so they're not fixed. Are our systems more or less complex than things we build them from? Generally, I'd say yes, because we build our simple systems out of just a little bit of code. We say, yeah, we've built our system, we run the code. Of course, we're going to attach some data to that. That makes it a bit more complicated. But there's loads more going on. We've got interfaces for the users, interfaces for applications. These things exist. Let's say they exist in a browser, but they exist in other things too. There's logging and error handling. There's various libraries that we introduce. Now, all of those things are different. We've not built them. They may be more complicated than what we're building. They may be more simple, but they interact. We wouldn't be using them if they didn't interact. They interact with us. Our thing, of course, lives in an operating system, maybe more than one operating system. It has people who use it, and it has people who build it. Anytime you introduce people into a system, it becomes more hard to fathom. And our systems have a purpose. They change over time. They have a value to them. And there are people interested in those things as well. So all those different interactions between people and tools and library and use and operating system and technology, and we're usually building, from my point of view, something simpler than the environment we're building it in. I'm tempted to say always. Always building something simpler than the environment we're building it in. And the thing that we deliver, the service that we deliver, needs to pay attention to that complexity. So I hope you don't get put off either by the idea of the basic pathologies. They're not in the systems, they're in you, me, us. And simple systems, we're going to talk about simple systems because those are the easy ones to talk about, to explore and to play with. That's not to say that you build complicated systems. They're fine. Let's move on. When we deal with a system, unless it's specifically built to lie, in which case we can often go and look at that. Sometimes that's my job. A system doesn't lie to us. A system surprises us. I think that's a crucial thing to think of. When you come across something where you think, well, that's not right, the system is doing exactly what it's been asked to do. We are surprised by that. Let's rephrase this. It's not that systems don't lie, it's that they are true to their nature. A system is built by us, it's constructed from various different things and plumbed together. It has a nature, and we'll explore what some of those natures are, and hopefully they'll make them a bit less confusing to me, maybe to you. The truth doesn't match some of the things that we intuit about simple systems. We believe that something that is easily describable has an easily describable set of properties, and that's not true, and I want us to look into that. We already know that the truth doesn't necessarily match our understanding. And sometimes as testers, that's what we do. We take an understanding, we make that into something concrete, which is an experiment. We call it a test, and we execute our experiment. And that experiment either confirms our understanding or refutes it. When it refutes it, well, maybe our understanding is wrong. The system is doing what we've asked it to do. What we understand about the system, maybe that's wrong, or maybe we need to go and tell the system to do something different. Maybe our understanding of how the system would interact is not what we would hope. And finally, I think this is important. When a system tells us something, it is common in the world of teams and people and purposes and deadlines to actively avoid that truth, which is a frustration to me on a personal level, but I think that it's true and it happens. And being able to demonstrate unambiguously a truth or to anticipate something, even though we know we might otherwise be avoiding it, is, I think, a powerful thing for us to do as testers. So we're going to go to exercise 0. Now, I was briefly a physicist, and physicists have a trope called a spherical cow, where you take a problem and you take a real thing and you abstract it. And a spherical cow is a cow, but it is also a sphere with its mass at a point. In systems thinking, and I'm going to show you a book. This is, move it that way, Systems and Models by Helmut Bossel. It's one of several. It's a very handy thing. I'll refer to it a couple of times. Hartmut Bossel, sorry. Lots of systems are dealt with in a mathematical way. I don't intend to do that here. And in books like the Bloom book, which the name's gone out of my head, it's in the references, which you'll find on that webpage. People often talk about, writers often talk about bathtubs. So this is exercise 0, and it is a bathtub because bathtubs turn up in ideas about software, about systems. And this is a very simple bathtub. I'm going to bring it up in a complex way because that involves changing stuff on my iPad. Hey, there's my website. So this is a very, very simple system. It's a very simple system that looked a lot prettier at 9 o'clock this morning. Sorry about that. Here's my simple system. Please load up. Okay, just loaded some CSS it didn't load before. And typically with a large group of people, I will play some music and leave you to play with it. Now, that's because in a large group, I can kind of get a feel of what people are doing. And I can't get a feel of what you're doing because you're all disparate and widely dispersed, and you may not be there. You may have your feet up on the couch. You might be looking at this thinking, what's going on? I'm going to ask you to play with stuff. I'm going to ask you to play with this thing for just a couple of minutes, and it's going to go a bit quiet while I do, which is going to disturb people who come in halfway through, but that's okay. They can be disturbed for a couple of minutes. I want you to play with these two because I want you to assess for yourself which one is the tap and which one is the plug. This is a bathtub. It's got a tap and a plug. Which one is the tap and which one is the plug? I'll play with it myself, so there's some degree of animation going on, and we'll think about what it is doing in a couple of minutes' time. If you don't want to play with it, that's fine. I will go over it in a moment. But please do. I built it. No, please play with it, because I think that playing with something gives your brain a different space. It lets it absorb things in a different way. So please play with this one bathtub. Please work out which is the slider and which is the plug. I suspect that'll be fairly swift. When you've had a look at the slider and the plug, you might want to have a look at flow going in and coming out. Okay, so a minute and a half, let's say. I'll play with this so you can see me playing with it. That'll be good, won't it? Nothing at all. Nothing at all. But there's a button down here that says Start System. Oop, excuse me. Now when I start system, I've filled my bath up. It looks full. It's empty it. Fill it up slowly, fill it up fast. Empty it. Fill it up fast, empty it. Alright. So it looks to me like that's the tap. I've filled it to the top and then I've stopped it. And so this must be the plug. Ooh, that empties it. So I can fill it up and I can empty it. Whey! And I can... I say oh. This is my software. I'm saying oh for your benefit. I'm expecting this. Now it looks as though that one can set the level. Emptied it. It comes back up to that level. Oh. Okay, so I've got 15 seconds left of you playing. I probably should have told you to mute beforehand if you don't want me to narrate. Never mind. For those of you watching in the future, maybe one of you muted it. Right, That's a minute and a half. I can't see anything turning up in the Q&A channels or in the chat channels, so I'm going to switch that over from all panelists to all panelists and attendees. Nope, still nothing. So I'm assuming either you've all gone home or you're playing with this.
Don't worry, if there's anything, I'll let you know.
Thank you very much.
That's my job, man. I need to have a job.
Excellent. Thank you, Joel. You got my back.
Wait, there is actually a question. Oh, sorry, a Q&A comment by Carlo.
Is it doesn't work on my machine?
No, close enough. It says up is tap.
Up is stuck. Oh.
No. Up. Oh wait.
Up is
the tap.
Ah, the top one is the tap. Yes, it is the tap. Absolutely right. Thank you very much. Yay, congratulations. Woo. So yeah, that's the top one is the tap. Let me but this thing has an odd relationship, and its odd relationship is that I have people tell me, and this isn't a trick, this is what they tell me. They tell me that this one sets the level of the bath because it does. Ooh. And it sets the level of the bath when I've got the tap open, when I've got the plug open. When I've got the plug shut, it just fills the bath up at different speeds. So I've got these two things. Now, let me show you one thing that I didn't show you before. Let's fill this bath up. There we are. Filled it up with the plug shut. I'm going to turn the tap off. If I empty it, how does it empty? It empties non-linearly. It empties fast at the top and slow at the bottom, as a bathtub does, which is one of the reasons why bathtubs get used. This is a spherical cow-style bathtub. This is a bathtub with straight sides, but even then, it would flow out faster from a deep bath than a shallow one. Let's watch. Flow out. The bottom is slow. But how does it fill up? Well, it fills up linearly. So you've got these two things, and they are working slightly in opposition. One with water coming in, one with water going out. The water coming in comes in at a constant rate that you can change. The water going out goes out at a rate that is set by how much water is in. And those two things interact to make this top control feel like it's setting the level. And it is. And that's an emergent property. That comes out of the way these things interact. So this is the simplest possible bathtub, and it is an illustration, I hope, that simple things can interact in ways that surprise us, particularly looking at the Q&A, which now I can see the drain is non-linear. Drains are non-linear. Sorry about that. They aren't non-linear in spherical cow-style physics. They are non-linear in the real world. That's one thing that this drain has got. It's non-linear. It goes out fast for a deep bath and slow for a low bath, which you will see, I hope, in your own baths. Brief break for you to go and check out your bath. Moving on. We're going to go back to the slides, if the slides will be gone back to. Technology is a new thing. So that was exercise 0. That is a bathtub. It is a basic kind of thing. And I hope that it is something that is showing you that two things can interact in a way that is not immediately intuitive. And the reason that's important to me is that I think that as a tester, I am a systems analyst. I need to analyse the systems that I'm with, not just the systems that people want, but the systems that I'm with. I'm given a system. Generally it's a software system, but increasingly it's involving hardware and networks and plumbing and you know what I mean. I work with how things seem to be, and I also work with how things are, and I have to squish those two things together and think about what's different about those two things. So systems are systems analysts. I want to take you to, again, Hartmut, get his name right, James, Hartmut Bossel's model of systems analysis, which is on page 1, I think, of this book. Shows you how far I've read. There we are. There's page 1 of his book. I was going to put this on as a photo, but I don't know how we are for copyright, so it's there as a video. You go and buy his books, great. And I'm going to draw you a picture of that to be kind of more live than I might otherwise be. Here is his model. We've got a system here. That's a system. It's a nasty pencil to write in, but anyway, never mind. And we've got an output of that system and an input of that system. In there you'll assume that it's out on the other end. Now, as testers, as experimenters, we are able to query parts of this system. And a lot of kind of classic testing says, all right, I know what my input is, and I know what my model is, or at least I know what my system is. It's sitting in front of me. What happens if I do things to it? What happens at the other end? And so I think we've got some sense in which testing looks at the outputs when we adjust the inputs and looking at a system, looking at a known system. We've also got a couple of things. We've got our known system. Sometimes we've got some surprise outputs, and then we're manipulating the inputs to see what gets to that output, all the conditions, all the setup, all the plumbing. That is something that I would think of as diagnostics. And to be complete, well, what happens if we know the input and the output? Well, in that case, we're doing some modelling. We're saying, okay, I put this in for my test, and I got this out, and that's true. So what's in the middle? What's the model? I realise my hands are going the other way, the other direction from my thing. So we've got these three parts, I think, to inquiring on a system. We've got something which I'll call test. Other people would call it different things. I'll call it test for the hell of it for now. We've got diagnosis, and we've got modelling. And each of those three things is a different inquiry on our system. We're making lots of inquiries on our system to see what we've got. We can come up with a diagnosis of what we need to do to make something happen, a test to see what might happen, and modelling to see what on earth could produce this. So when we have a system, then it has these emergent properties. And when we model a system, we need to think about how that works. I want to show you a bicycle. This is not a real bicycle. This is a robot bicycle. It's not even a robot bicycle. This is a simulation of a robot bicycle being ridden by a simulated robot. And that simulated robot bicycle ridden by a simulated robot is ridden by a simulated robot with two neurons. And this is a picture of an aggregate of, I think, 800 runs of this particular model. And you can see that although it looks symmetrical, it's not symmetrical. No, look here and here. Those threads are different. Up here, it's not symmetrical. It's symmetrical in aggregate. That symmetry emerges from something that's going on. Other things that emerge, well, there seems to be some kind of arc of failure here. If that's where the bicycle spins out, its first turn seems to be here. It seems to have an arc of failure. There seems to be failing there too. These things seem to go in this way round. There's generally, however far they get, this is quite narrow, but then falls over again there. It goes narrow. We can start to see emergent properties and patterns from this two neuron simulated robot riding a simulated bicycle. These properties of how the robot rides the bicycle emerge, and they emerge from a system because a system has properties that we don't necessarily see on one run, and so we have to aggregate to look at that. It's at this point that I think I've shown you the Hartmut-Bossel book, so I'm not going to show you that. Well, I'm sure there are two of them. So there are many systems that Bossel wrote about in several books. One of them is called System Zoo, which has plenty of different systems that move it that way, James. There, plenty of different systems that are interesting to study. And his big book on systems is Systems and Models, Complexity, Dynamics, and Stuff. Right. Put those away. You'll find links to those in my references webpage. Surprise! If you go back to that webpage and scroll down, there's loads of stuff there. Looks lightweight, probably is. So bicycles. This bicycle has a set of emergent properties, and when those properties emerge, we start to see things happen that we might not necessarily expect, but they fall into certain families. Let's go back to me drawing pictures again. Go sideways. So one thing that happens if we draw a graph and we say that time goes this way, that is a t. It's just I pressed a bit too hard because of nerves. T. Yeah. So we've got a graph of how something operates over time, or maybe how it operates in aggregate, and some things do this, and they seem to go up as time goes on, and some things do this a bit more. Now, unfortunately, being the situation we're in at the moment, you start to recognise this as an appalling curve that is filling us with fear. Ultimately, it does that, and it goes up, and it goes up and up and up, and we worry about it, and we think that it will go to infinity. And of course, that's not how systems work. This is an exponential curve. Systems demonstrate these exponential curves. But if you look at a real system, not a model of a system, and the situation we're in is one of those real systems, it goes up exponentially, then it does that, because it hits a constraint. So one thing that we come across is that a system can seem to explode, but then its explosion is caught by something. And that often tells us where the edges of a system are. Hang on, we've got something where our model says this should explode, but our system doesn't explode because there's a regulator, and that regulator is in the outside world. Perhaps it's the number of things that it's possible to infect, or it's if this is a resource usage, if it hits the limit of a resource. So things that look as if they're going to explode, generally you find a resource limit with them. Another pattern that happens is the exponential decay, where something seems to want to go to zero. Now again, in the model it might never actually go to zero, because that's how the maths works. But in the real world, things tend to be quantized. Again, if you're using resources, there's something called a predator-prey relationship diagram, which predicts all sorts of interesting things that look as though they might sustain themselves until you have limited resource, until you have something where you can't have less than one of. The predator-prey relationships famously look at wolves and bunnies. You can't have less than one bunny. At which point, in fact, if you have less than two bunnies, of course, you can't then increase your stock of bunnies, and then your wolves die off. Go look at the predator-prey relationship for more around that piece of wolf-bunny jargon. You've got these curves that look like they go to zero. They actually do go to zero, and then they can't come back up again. So you've got things that die. Those are two things that turn up with systems that we're looking at. But you also have some funnies, and I'll go into those in just a second. There are funnies where systems do this. They wobble. And sometimes they kind of jitter. Or worse yet, just do random stuff. And even more strangely, sometimes the systems synchronize. So you've got one system that's doing this, and another system that's doing this, and you think that's fine, they're not in sync. But after several hours, they're in lockstep. All those things arise from system dynamics and can be understood in terms of system dynamics, and I think it's helpful to us to have that understanding. So let's go and have a look so that we can anticipate where things overshoot or oscillate. Right, back to slides, then back to toys. Slides are there. There we are, back to the bicycle. We get properties from interactions. As testers, we get quite used to dealing with things in parts, particularly if we're looking right down at the code level of things. I want us to be thinking about the relationships between those parts, and more, the relationships between those parts over time. So now we're going to get to exercise 1. This is a bathtub that fills itself. We give it a level, and this bathtub fills itself to a level that we set. I'm going to flip over to it, I'll play with it, and then I'll come back to you guys. I'll try to not talk through. Well, I am going to talk it through for those people who don't want to mute. If you want to explore, maybe mute, maybe don't. Up to you. Right, toy 1, one tank, one flow. This is the toy. It's looking better than the other toy, although it's still not great. I don't think we need to start and stop this one, so let's have a play. I'm going to play first with my goal. My bathtub follows my goal. Although, note that it is laggy. There is a delay. And in fact, you've seen that with the previous bathtub. When we looked like we were setting a level, we weren't setting it immediately. There was a bit of a lag. And that's important. A little bit of a lag means there's something going on. So, okay, if I move that around, it catches up. Let's see, if I increase that sensitivity, yeah, it goes a bit faster now, but look at it, it overshoots a touch. Make it more sensitive, it overshoots more. Wah! So that's something interesting. Now, let's have a look a bit further down this page. Here's a picture, not of what it's doing now, but of what it might do. We'll come back to that in a moment. So there we go. I'm fiddling around with my goal. It does those things. And then I've got this nasty one, feedback length. Let's just see what it does. Nothing. Until I move the goal. And that seems to be wobbling. Shut up. Don't do that. Don't do that. Don't do that. Don't stop. Oh, look. So I've got a wobble there that if I increase the sensitivity, the wobble increases. I decrease sensitivity, the wobble decreases. What happens about the length? Let's give myself a wobble. There's a wobble. Oh, it's banging on the top and bottom now. Alright, I think the gold's not helping me. How are you doing with yours?
Well, I had a lot of fun.
Oh, cool. That's what it's for. So let's get back in the room. Let's have a think about what we saw here. We've got three things here. We've got a red line. That's the goal, and we tell our bathtub to do that, and it's an inefficient bathtub. It throws water away. It's sensitive to feedback in some way, but we've got some curiosities around that sensitivity to feedback. If we make it more sensitive, it's actually a bit likely to go a bit random. Wallop, 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 wallop's getting bigger. Is it getting bigger? No, I found it's kind of a medium setting. Let's increase the delay on that nasty one. That's just miles off. I'm glad that's not my bathroom. Let's wind that back a bit. If we have a look down below, then rather than looking at something jumping up and down, which is very difficult for us as testers to comprehend, and difficult for us as humans to comprehend, I've drawn something that's going to be a shame. I've drawn something that is going to hopefully help us to appreciate this over time. Excuse me, I'm just going to plug my pencil in. I'll do this with the rest of this with my finger. We've got something that says, well, over time, this would seem to fit what we've got. But if I increase the sensitivity, we'll see that it gets wobblier. If I increase how long it takes to get things right, we can see not only does it last, well, not does it take a little bit longer between the wobbles, but the wobbliness lasts a lot longer. So we've got some characteristic things here. Have a look at that amplitude as we move the goal up and down. It increases in the size of the wobble. So we've got some stuff that I think that we should start appreciating and understanding. Let's just drive this a bit hard. It's going square at the top now. So now we're looking at not what our system is doing in the moment, but what it might do over time. We know that this is going to be a system that goes a bit nuts. Let's move my goal. There we go, off it goes. It's getting bigger because it's damping at the top and bottom. That's now entered into a massive oscillating state. This is to do with its nature as a system that has feedback in it. Now, feedback is a really, really crucial part of where we come from as testers, because I think, again, I don't know Helmut Boss, but anyway, the next time he brings up his model of systems, it's got this feedback loop inside, and it talks about systems being dependent not just on their inputs and outputs, but also on particularly the feedback within them. And as testers, we need to think about feedback and find how we can manipulate it. I sometimes go hunting for bugs, and one of the things I look for is feedback. One of the things I look for is something where when I put something in, it turns up somewhere else, and perhaps it gets worse and worse. So let's say I'm testing an error handling system. My error handling system takes everything that's errored out. Let's say it's processing a whole bunch of stuff. Everything that's errored, it sticks into a file. And it says, I'll deal with those later. And it's dealing with 10 a day or 20 a day. Chunker, 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 it goes. And then I get a bigger problem. And then rather than getting 100 into that file, I get 1,000 into the file. That's fine, the file can cope with 1,000. But the system that processes the file doesn't cope very well with 1,000. It takes a bit longer. And then it starts to have trouble, so much trouble that the system that's processing the records can't process the records because the system that's handling the errors starts to take the resources. So then rather than having 1,000 errors, which may have come from outside, I'm starting to get errors because I'm handling the errors, and everything just inflates enormously. That's the kind of thing I look for as a tester. I look for points of feedback, ways that I can manipulate it, ways that I can mess with it. Now, when we build systems, we respond to these points of feedback. Somebody sees what I do and goes, right, yep, we need something in there to handle our error handling, and they build something and say, if the rate of errors coming in is fast, then we'll cope with it. Or if the number of errors is large, then we'll cope with it. And that brings us on to something different. Excuse me, my iPad is turning off. That brings us on to something a little bit different.
James, heads up, we have about 12 minutes.
That's okay. I'm on to my last two things to show,
okay,
which should take between them about 5. Cool. Let's try. So when we've got systems that have got things that respond to rates, we've got a whole new set of weirdnesses, and they sometimes go under the name of deterministic chaos. Now, I can't build things that have deterministic chaos, so I've gone to Dirk Brockman. Shout out to Dirk Brockman. His stuff is brilliant. You'll find a link to his things. Let's flip back over to these, and I'll show you a bit of deterministic chaos. So deterministic chaos happens to jerk systems. What's a jerk system? Jerk system is one where you're responding not to how something changes, but to the rate of change. That's difficult to think of, but think of this. My position is one thing. My speed is how much my position is changing. My acceleration is how much my speed is changing. Jerk is how much the accelerator is changing. So think of a jerk system as one where you can slam on the accelerator or the brakes, and then weird things start to happen. In maths, you need a certain number of, get called degrees of freedom to start seeing this. The most simple way to demonstrate this is a double pendulum. This is a double pendulum. I'm going to turn on a couple of things. I encourage you to turn them on as well. I'm going to turn on trace. I'm going to turn on ghost, and the reason for that is something I'm going to explain. Deterministic systems are the same every time you run them. Something that exhibits deterministic chaos is the same every time you run it, except that it's enormously sensitive to starting points. Now, this thing is sensitive to something that is described as the size of a bacteria on the end of your finger. Well, we can't envisage that, so I did a tiny bit of maths. It's roughly the size of a phone when you see it from about 10 kilometers away. So the difference between the ghost and the thing that you're going to see is the difference that is to do with the angle that you would see if you looked at a phone from 10 kilometers away. Let's start this process off. Here we go. My double pendulum swings. It's going to exhibit weird behavior, but it's deterministically weird behavior. And it's going and it's exhibiting this behavior. You can kind of see how it's going to go. It's looking fairly weird, but there's the ghost. I hope you can see it on your systems. The ghost is currently matching. We're only 2 cycles in. And now the ghost is deeply not matching. And now there's a moment and we're on a totally different trajectory. I'll remind you that the difference in that error the difference in that setup is minuscule. It's the kind of difference in angle you might see looking at a phone 10 kilometers away. It is, I think it's 0.0001 rather of a degree. It's very small. And the point is that this system with deterministic chaos exhibits stuff that we can determine, but it's so sensitive to its initial starting point that it does all sorts of weird things. And this is another simple system. This is just a pendulum, has to operate under gravity because that's one of the degrees of constraint that it's got, and it's exhibiting this strange chaotic behavior. As soon as we start to build systems that pay attention to weird cases, so we're saying, oh, this has got too big or it's got too big too fast, we enter into a world where we might be seeing some kind of chaos, not in how something operates, but how something is sensitive. Let's go and have a look at another. I want to pop back to my slides to make sure we're in the right kind of place. We've had a look at deterministic chaos. Final thing I want to look at is surprise synchronization. Now, with these systems, it's been kind of strange how they've disappeared off and become unexpected. This is the opposite way around. This looks at systems that somehow gather themselves together into a kludge. And I've seen this when I've been testing switches, so that's big telecoms things, where you're expecting everything to work because all sorts of things are randomly distributed, and you don't ever expect them to be all lined up, but they do. Let's have a look at how that might work. Go over to Nicky Case's stuff. Nicky Case is another person who builds amazing explorable things. I can't build his things, so I've nicked his. This is Fireflies. This might or might not work on my iPad. Hopefully it'll work for you. It did when I tried it earlier on. Here are a bunch of Fireflies. Now, the thing about these Fireflies is they've got a random flash. I'm going to just switch them over to clocks because that makes it easier for us to see, perhaps, that they have a random flash that happens when that little clock bit points upwards. I'm hoping this works okay over the bandwidth we've got. And I'm just going to turn something on and I'll talk about it. It's called Nudge Thy Neighbour. Oh, that was quick. Right, so you can see they're all happening in sync now. The reason they're happening in sync is that each one of them is paying attention to something that flashes. So they're going around. Let's just reset that. Turn that nudge down a bit. Reset the Fireflies. There we are. And they're going to start nudging each other again. And there they go. They're flashing in sync again. The only thing each of these clocks is doing is paying attention to if one nearby clock flashes at a time when it's not flashing. And if it does, it brings its flash forward a little bit. That's the only synchronization they've got. This is not a central synchronization. This is an emergent property, this emergent flash. So that's my last two illustrations. They're not necessarily for you to play with in the same way as the other two, but I hope that you'll find that useful. We've looked at how things can become complicated, even though they're simple. We've looked at how something that just pays attention to one or two other things can start to synchronize with it. We've looked at how tiny differences in starting points can make a world of difference in how something actually behaves over time. We've looked at how feedback can result in resonance and how that resonance can increase as feedback does. And we've looked at how two things, simple, linear and non-linear flow, can create something that has a delay in it and that appears to be doing something that is actually an emergent property. Each of those things is a complication. Each of those things is a complication that wouldn't necessarily be anticipated in the system design. So, if there's one conclusion from this, it is that as testers, we need to pay attention to complication. We have a tendency to forget that it's possible, to not see that through our intuition that it's possible, and when it turns out to be truthful, to want to ignore it corporately. So please pay attention to complication. That's the end of my presentation on basic pathologies and simple systems. The pathology is us, and we can get around it by paying attention to complication. Those are my details, and there's the page that you've been playing with. I think that gives us about 5 minutes to answer any questions. And Joel, I'm over to you and stuff that we've got going on.
I need to say that this is like the first time that we had such a active session on the online test. I'm still trying to process it, even as a tester. It was fascinating, and I loved it. In a word, that I loved it. I'm trying.
It's hard to bring interaction to these things when you don't have anybody to interact with.
Well, I'm not sure if it's because of your corona hair or something else, but it actually worked. I was playing around with it, and I will. Okay, just to give you again, no one is hearing, so I can actually say to you. You might see that I have a guitar here in the background, and usually when people are talking, I take the guitar and I practice my guitar. I started with it, and then we started playing with this. I just set it aside and started playing myself. I loved it, and I actually think that it helps a lot, especially when we're trying to understand, hey, we have those types of irreproducible bugs because we see that chaos happening around us, and you're making it very tangible to understand. It might look like chaos, but it's not, because we're working with deterministic systems. So no, don't give up, and I think that that's a pretty amazing lesson. and I really liked it.
Thank you.
I'm trying to see if someone else actually managed to have any questions, because again, you basically showed us what we need to do.
I've got one, and it's about, should we build complicated tests? And there we are. When you say pay attention to complication, are you saying that we should build complex tests? I think that when I look at the tests that my coders build me, they're often extraordinarily simple because they don't pay attention to very much data. They just pay attention to one bit of data under one circumstance. When I go in to test these things, I tend to build probes. And so I cope with the complexity of a system by introducing the complexity in my brain, I hope. And I tend to want to visualize things because that's a way to get loads of information into me all at once. Should we build complex tests? I don't know. Should we build broad experiments? Yes. Yes, we should. And I like the idea of broad experiments and human brains as being part of the way that we test. I'm not convinced that a complex test that seeks to extract my judgment and put it into something that perhaps has a lower daily rate is of any use. There are better things to do with computers. So thank you to anonymous attendee. I've got one from Dimitrio who says, build communication between board and testers. How do I draw parallels between complexity of system? Well, I don't think I've mentioned the boards. I do talk to boards quite often. Boards are very happy with things being a gamble and with people being involved and that itself being complex. Boards are not as happy with testers coming to them and saying, hey, you've got another complex problem. So once we get over that initial, you're telling me this is really complicated, well, I'm telling you I can deal with complexity and come to you with simple stuff, but understand that sometimes the things I'm going to come to you with will require your skills and complexity to engage with. It's not a did we pass, fail, there's more complexity to that. Then I find boards are generally receptive to that. Treat the boards like grown-ups, they'll treat you like you're worthwhile.
I'll try to remember that next time I need to interact with a board.
Well, sometimes they just kick you out because that's what boards do. That's just my experience, of course. That other people, but you may not get kicked out like I get kicked out of board meetings, but it happens.
James, we're actually at the top of the hour. I again wanted to thank you.
Okay.
It was an amazing session, and based on the comments here, I think that everyone actually saw it as well. So thank you a lot for it. And again, if anyone has any additional. By the way, I placed the link in the Slack channel so that everyone can actually go into there, go to your page and take it in there. And if anyone has any additional questions, comments, complaints, go into James's Slack channel and just hit him in the head with it. I'm sure that he will do it.
I'll go into Slack now. I'll deal with stuff. Thank you all very much.